Okay, so welcome back. Today we're going to look at the compressibility factor. This is really the word used in academics, but in real life is more known as the compression factor. Okay, so what is this about? As we all know, nothing is perfect. Okay, so the compression factor is actually related to the ideal gas, as you will see. So the compression factor is a factor which describe the deviation of a gas from the ideal gas behavior. Okay, so we all know the ideal gas relation. Which is what? PV equal nRT. So this is one option, but if we use the specific volume, so N we know is the mass divided by the molar mass, this becomes what? N divided by molar mass RT. So we can just rewrite this as PV divided by M equal to MR divided by MT. And this will give us the second form of the ideal gas relation, which is pressure times specific volume. Oops, this M is gone, sorry. I'll move it to the side. Times R bar, which is the ideal gas constant for the specific gas, T. So the two expressions we have for the ideal gas at PV equal nRT or PV equal RT. Okay, so if a gas behaves as an ideal gas, what does that mean? Basically, it will mean that the ratio PV equal divided by nRT should be equal to 1, okay? Which will be the same as saying that P, specific volume, divided by R bar T, this should be equal to 1. But if it deviates, that means that it's not going to be equal to 1. So basically, this is Z, which is the compressibility factor. So basically, we say that if it behaves like an ideal gas, these relations are true, so Z equal to 1. If it deviates a little bit, Z will be generally lower than 1. Okay? And all this data actually is obtained experimentally. The fact to find if a gas deviates from the ideal gas behavior is found experimentally. And they have some curves. They have some in the book, but it's really hard to see anything. This is actually the figure. I can zoom in if you want, but it is really hard to see. Let's see. Okay, I'll zoom it over here. So I decided to just take one from the book, this one. So basically, what does it show? It shows that this is Z, and this is of a factor which is PR, that will see what it is, and this is TR. You see that the curve will be about 1 as the ideal case, but it's not really a straight line. It follows like some type of parabolas over here. They're not really parabolas, and these are all the different gases. So all this data is obtained experimentally. So now I'm going to explain how to use these figures. So in order to know how to use this figure, we need to determine TR and PR. So basically over here, what do we have? So in order to determine Z from figure on the table will be A15. Okay, I will attach it. We need to define two parameters. So we have PR, which is equal to P over PC, and TR, that is equal to T over TC. So over here, PC is the critical pressure, and TC obviously will be the critical temperature. Okay, so on the problems, generally we are given P and T, and then those two critical values I can obtain from a table that will be given in table A1. If you look here on the left hand side, you have different ideal gases: air, ammonia, argon, so on, and then you have the critical point properties. And here you will see the critical temperature and the critical pressure, and this would be the critical pseudo specific volume, but we'll see that later on. Right now we're just interested on the T and the P. Okay, table A1. So we can say that these two values over here will be obtained from table A1. Oops, let me zoom out now so you can see on the page. Okay, before we do an example, let me just define the principle of corresponding states. The Z factor, which is the compressibility factor of all gases, is approximately the same at the same reduced pressure and reduce temperature. Okay, so basically That's the reason, if you look at this figure here again, that even though we have all different gases over here, you kind of see that they are kind of located about the same location. Okay, so that means that you don't need to have each one of these curves for every single gas, because since those properties are more or less constant at the same PR over here and TR, we can just use one figure. And that's the one you have actually in figure A15 of the tables. I try to zoom in a lot more now. Okay, the best thing is that you print it out. But basically you have at the bottom, you have PR, here you have the Z, and it's really hard to see, but here you have lines of TRs, but you're also going to have lines of VRs. But that would be later. If you look at it, the dotted lines are actually VRs, you can see right here, and the solid lines would be lines of TR. Okay. So let us do a simple example. Let me zoom out. There we go. So example. Oops, let's see if it, okay. Determine the specific volume of refrigerant 134A at pressure of 1 megapascals and a temperature of 50 degrees Celsius using A, B. So first part will be using the ideal gas relation. And 2 will be using the compressibility factor or compression ratio. Okay. So maybe before we start the problem, let's go get the data that we need. So we can say from table A1, which I will show you now. Here we go, table A1. If you go to the bottom, I don't know if you can see it here, see if I can zoom in. It's not really zooming. Okay, so I zoom here, you see the R144, they give you the chemical equation, and then this is the 102.3 is the molar mass, and the 0.08148 is the gas constant. And then on the right hand side of the same line will give us a critical temperature of 374.2, and the critical pressure will be 4.09. Okay, I know you cannot see the top, but because the top, as you can see, will be the temperature, the pressure, and this would be the gas constant. Okay? It's just hard to see if I zoom out. So let me write that information. So from table M1, we have that our R bar will be 0.08149 kilojoules per kilogram Kelvin. The critical temperature we say was 374.2 Kelvin, and the critical pressure 4.059 megapascals. Okay, so part A, using the ideal gas relation, so I use the form P specific volume equal RT. This will just tell us that the specific volume is equal to R bar T divided by P. Okay? So if we do the numerical application, they give us that the specific volume using the ideal gas relation equal to 0.08149 times the temperature in Kelvin, the temperature was 50 degrees, so it will be 273 plus 50, we need it in Kelvin. Remember, this is this temperature here. T equal 50 degrees Celsius, okay? And P is equal to what? 1 megapascal. So we need this in kilopascal, so 1 megapascal will be 1000 kilopascals. Okay, that way this will cancel with the units of kilojoules. Alright, so if you do this calculation, you get that the specific volume is equal to 0.02632 cubic meters per kilogram. Okay, and B now is using the compressibility factor. So in order to use the compressibility factor, we need to determine PR, which is the reduced pressure, P over PC, okay, I think I did not mention before, but this is the PR is the reduced pressure. Okay, and TR will be the reduced temperature. Okay, so this will be equal to what? This will be equal to 1 megapascal divided by the P critical 4.059. So this is equal to 0.2464. And the reduced temperature is T over T critical, which will be the 50 plus 373, which is 323, divided by T critical, which is 374.2. And that gives us 0.8632. Okay? So now, from figure A15, but to tell the truth, in this problem, I use this figure here, which is from the book, and if I zoom in, you see that it's only TRs here for 1. So I kind of make up, my guess here for the 0.86, TR equal 86. So these are lines for different TRs. So I made that one. And then 0.25, I put a kind of point over there. And my guess was that that is approximately, so from figure at PR TR equals 0.2464 and TR equals 0.8632. I get that Z approximately equal to 0.85. Okay. So basically, what does that mean? So that we know then that the final specific volume using the compressibility factor will be equal to Z multiplied by the 1 of the ideal gas. Remember, the Z indicates how much is deviating from the ideal gas behavior. So this is the ideal gas behavior, and this will be the one with the compressibility factor. So this will give us that this is equal to 0.85 times the initial value that was 0.02632. Okay, so this will give us that actually the specific volume, if we look at the compressibility factor, is equal to 0.022372 cubic meters per kilogram. So you see that really in real life, this compressibility factor is not really used in academics much. But you see that if you don't take that one into account, you can do errors of up to what? 15%, no? Okay? So now I'm just going to finish with one more thing, and is in some cases, so this is really not that important, but I'll put the sign right here. But like when P and the volume V, or this could be the specific volume, or T and volume, again this could be the specific volumes, are given, instead of what? P and T, which is the problem we did, the compressibility figure can still be used but the pseudo-specific volume VR is required. Okay, so basically the VR is just defined as the specific volume divided by R T critical over P critical. And basically the procedure is exactly the same as we just did, except that if you go to the figure A15, like I mentioned before, is hard to see. Let's see. Okay, you found the contrast. So you see that you also have lines of VRs over here. So you can just look at the value of Z and then the value of VR and P or T, and then remember the solid lines over here are different values for T. Okay, TR. So this will conclude this video. Again, this is important if you are in working in industry, but in academics, really the specific the compressibility factor is not used that often. Thank you for your attention and have a nice day.